Salam and welcome everyone. So today we're going to be working on the question on the screen that says the molar entropy of a sample of neon at 298 Kelvin is 146.22 joule per mole Kelvin. The sample is heated at constant volume to 500 Kelvin. Assuming that the molar constant volume heat capacity of neon is 3 over 2 R, calculate the molar entropy of the sample at 500 kelvins. So the first thing you have to do whenever you have a question like this to write out the parameters. We're told that molar entropy of a sample of neon at 298 Kelvin is this. So the molar entropy at 298 Kelvin is 146.22 joule per mole Kelvin. The sample is heated at constant volume. So this is a constant volume process. Okay, so the change in V is equal to zero, meaning throughout the entire process, the volume is going to be the same. And we also know that they said that the sample is heated. So it's an increase in temperature. So it's increased to 500 Kelvin. Assuming that the molar constant volume heat capacity of neon, or assuming the molar heat capacity at constant volume of neon is 3 over 2R. So that would be CV, comma M is 3 over 2R, which is the same thing as 3 times 8.3145, okay, joule per mole Kelvin divided by 2. Okay. We're now asked to calculate the molar entropy of the sample at 500 Kelvin. So this is actually what we're looking for. What I'm about to box right here, that I'm currently boxing, is what we're looking for. And we already know that we have an initial temperature, okay, of 298 kelvins and a final temperature of 500 kelvins. What we're actually supposed to be looking for is the molar entropy of the sample at 500 kelvins. So to continue our work with the CVM, we have to remember that CVM is just 3 over 2 times 8.3145. When we put this information in a calculator, we end up getting 12.4718 joule per mole Kelvin. When we have this information, our work is still not done. We just have to basically note that when you have a question like this, we have a formula that we use. The formula that we use is simply this one right here, which I'm writing. So the molar entropy at final, or the molar entropy at the final temperature, is equal to the molar entropy at the initial temperature, okay, plus the molar heat capacity at constant volume. If this is a question where we have constant pressure, is going to be Cp, comma m. But since it's a constant volume question, we have Cv, comma n. So you have ln times ln, the T final divided by the T initial. So that's the case here. Now we just have to simply substitute. We have to simply substitute. So we have S 500, okay, Kelvin, which is what we're looking for, is equal to the molar entropy at the T initial. So the initial temperature is 298 Kelvin, and the molar entropy at that particular point is what we have here, 146. So that's basically 146.22 joule per mole Kelvin. So all of that plus CV, comma M, so that would be 12.4718 joule per mole Kelvin. ln, so times, okay, ln T final divided by T initial. So T final, that will be 500 kelvins divided by 298 kelvins. So that's basically how it's done. You cancel Kelvin here, you cancel Kelvin here, and then we just continue our work. So we have S500, or molar heat. Honestly, you can write SM, you can write S. Just make sure you understand that what that SM or S signifies is the molar entropy. So you have this 500. 500 is just going to simply be this 146.22 joule per mole Kelvin, okay, plus 12.4718 joule per mole Kelvin times, so this information here, times ln 500 divided by 298 is just simply 1.67785. So there's that. And yeah, times that. So what we end up with is just basically SM 500 kelvins, just 146.22 joule per mole Kelvin plus 12.4718 joule per mole Kelvin, okay, times ln 1.67785, 785. When you input this information, this second part of the information after the plus sign, in the calculator, you get that to be 6.4543 joule per mole Kelvin. So when you add them up, the molar entropy at 500 Kelvin, you get 146.22 plus 6.4543. When you add them up, you end up with 152.6743 joule per mole Kelvin. Now, when we go back to the beginning of our question to be able to know what we're working on, sorry. So when we go back to the beginning of our question, we're going to see that the molar entropy at 298 Kelvin given to us was 146.22. This was in two decimal places. So we're just going to simply put our answer in two decimal places. So what we end up with is molar heat capacity, sorry, the molar entropy at 500 Kelvin just is 152.67 joule per mole Kelvin. And I also wanted to mention that it's possible that you could also write this in three sig figs because we have 298 Kelvin here in three sig figs. In case your professor asks you to solve this in three sig figs, what you end up with is just simply the molar entropy at 500 Kelvin is 153 joule per mole Kelvin. So this one is in two decimal places. This one is in three significant figures. If you have any questions, please put it in the comment section. If you're a student who is trying to succeed in all your STEM related courses, make sure you email me at shohabitutoring@gmail.com. I help students in middle school, high school, and college succeed in all their STEM related courses, as well as I mentor students to be the best version of themselves in their academic life. I wish you guys all the very best. Make sure you like and subscribe. Assalamu alaikum wa rahmatullahi wa barakatuh.